In this video, we will talk about zeros and poles. In particular, we will start with zeros, and we'll talk about classifying zeros according to their order. The next thing we will cover is creation of poles from zeros. So in other words, we're going to look at special functions that we can write as a quotient and talk about how the zeros of the denominator become zeros, and in a very special case, when we have a simple pole, we have this quick formula for calculating the residue of simple poles of these quotients that satisfy certain conditions. So this is our overview slide, which we'll spend about 5 to 10 minutes on before we go over each topic in more detail and with more examples. We will start by talking about how zeros and poles are closely related. We will see how poles are created from zeros, which is not a difficult thing to imagine, because if you have a polynomial with zeros, you just put that polynomial in the denominator of a fraction and you'll get poles. So our first topic will be zeros. And we define zeros by saying, suppose we have a function f that is analytic at a point z naught. Since f is analytic, all the derivatives fn at z naught exist at z naught. Now, if f of z naught is equal to 0, and if there's a positive integer m such that the mth derivative at z naught is not equal to 0, and each derivative of lower order vanishes at z naught, then f is said to have a 0 of order m at z naught. I will illustrate that with an example here where f of z is equal to z cubed minus 8. So we can set this function equal to 0, and I factor it some so I can find where the function is equal to 0. And my zeros are z naught equals 2, and z naught is equal to minus 1 plus or minus square root of 3i. And for now, we're going to focus on z naught equals 2 because it's easy, not because the other ones aren't valid. But now if we want to find out what is the order of that 0, well, that's the first mth derivative such that the mth derivative at z naught is not equal to 0. So here we have f prime of z then is equal to 3z squared, f double prime of z is equal to 6z, and f triple prime of z is equal to 6. When I plug in, and the fourth derivative is equal to 0. Now when I plug in z naught equals 2 into f, I get 0. That's what makes it a 0, the function. When I plug it into the first derivative, I get 12. This is not equal to 0, so that means the z naught equals 2 is a 0 of order 1. We have this alternate way of characterizing zeros, of determining what order the 0 is, using this theorem. Let a function f be analytic at a point z naught. It has a 0 of order m at z naught if and only if there is a function g which is analytic and non-zero at z naught, such that f of z is equal to z minus z naught raised to the m times g of z. To illustrate this theorem, I have this same example, f of z equals z cubed minus 8. This is the work we did previously to show that z naught equals 2 is a 0 of order 1. But now let's use this theorem here. So I'm going to propose z naught is equal to 2. That's the 0 we're going to look at. We can see that f of z is equal to, in this case, we're going to put it in this form that our theorem says, which is z minus z naught to the m, so that's z minus 2 raised to the 1 times g of z, which is now g of z is going to be z squared plus 2z plus 4, right? This is the g of z. When you multiply the z minus z naught to the first power, it gives you f of z. So now we can look at g of z. So what we're trying to determine if g of z satisfy the conditions of our theorem. So because the theorem says that this function f, if it's analytic, it has a 0 of order m at z naught, if and only if there is a function g that is analytic. So first, this function, it's a polynomial, so it's entire, it's analytic everywhere. And in particular, it's analytic at z naught. So it satisfies this first condition of being analytic and non-zero at z naught. And you can also see that it's not non-zero, because when you plug in g of 2, then you're going to get 2 squared 4 plus 4 plus 4, that's 12, which is not equal to 0. So the second condition here, that it's non-zero, is satisfied. And then last, we need to see that f of z is equal to z minus z naught to the mg of z. Well, that's how we constructed z, so therefore we would say that z naught equals 2 is a zero of order 1. Next on our overview slide, we have these two theorems here, which I really debated whether or not I wanted it on my overview slide because I'm not going to really cover them, but I feel bad about not at least writing out the theorems. The reason why I will not be covering them is because the main point of these theorems is it allows us to prove other results. We don't really use them in our problems. Then the last topic we have then are poles, or in particular, creation of poles from zeros. Suppose we have A, two functions p and q which are analytic at some point z naught. B, p of z naught does not equal to 0, but q of z naught equals 0. So q has a 0 of order m at z naught. Then the quotient p of z over q of z has a pole of order m at z naught. Then we have this following theorem that allows us to calculate the residue of poles that we have constructed by having this quotient of two functions. So let two functions p and q be analytic at some point z naught. If p of z naught is not equal to 0, and q of z naught equals 0, and q prime of z naught does not equal to 0, then z naught is a simple pole of the quotient p of z over q of z, and the residue at z equals z naught of p of z over q of z is equal to p of z naught divided by q prime of z naught. Our first example is to calculate the residue of f of z equals cotangent of z. To use this theorem here for a very quick way of calculating the residue, we need to have our function f of z written as a quotient of two analytic functions. So what I have is cotangent is equal to cosine of z over sine of z. Cosine and sine are both analytic. They're entire, so they're analytic everywhere on the complex plane. So far what I have in this theorem is now I've identified my two functions that are analytic, and in this case they're analytic everywhere. My two functions are cosine of z and sine of z. Then the next thing I need to know is where I'm looking for zeros, where q of z is equal to 0. So where is sine of z equal to 0? Well, sine of z is equal to 0 whenever z naught is equal to n times pi, any integer multiple of pi. So that's this part here. But I need to verify that p of z naught is not equal to 0. And that is true that p of z naught, which is equal to cosine and z naught n pi, well, that's equal to negative 1 to the n. So it's not equal to 0. So far we have this part of our theorem, that condition is met. Then finally we need to verify this last condition, that q prime of z naught does not equal to 0. But in this case, q prime of z naught is equal to cosine of n pi, which is also equal to, again, negative 1 to the n. So that's not equal to 0. So all these conditions are met. So what that tells us is z naught, that is z naught equals n pi, is a simple pole of the quotient cosine of z over sine of z. Then we have this formula for the residue is equal to p of z naught, which again is negative 1 to the n, divided q prime of z naught, which is negative 1 to the n. So the residue is equal to 1. So rather than going through and calculating the Laurent series, when you have a pole that is constructed by using this quotient, you can use this function here as long as these conditions are met. I spent a little more time than I intended to on the overview, but let's now go ahead and start with our first topic. We'll look at zeros in more detail with more examples. First, we have our definition of a zero, and in particular, we're going to talk about the order of zeros. So it's really a definition of zeros of order m. So suppose we have a function f that is analytic at a point z naught. Since f is analytic, all the derivatives fn of z naught exist at z naught. So if f of z naught equals 0, that's what makes it a 0. And if there's a positive integer m such that the mth derivative at z naught does not equal 0, but all of the derivatives of lower order are equal to 0, then we have the definition of a 0 of order m at z naught. To look at this definition, we're going to consider this first example f of z equals z cubed minus 8. First, to find the zeros, we set f of z, z cubed minus 8, equal to 0, and I'll factor it out so that I can easily identify our first 0 is z naught equals 2, and our second 0 will be equal to minus 1 plus or minus square root of 3i. So we have 3 zeros. To make life easier on me, we're going to first focus at z naught equals 2. So this is the 0 we're going to focus on, and we're going to look at what order it is. To do that, we're going to have to start looking at the derivatives f prime of z naught. So I have written down then the first derivative of f of z is equal to 3z squared. The second derivative is equal to 6z. The third derivative is equal to 6, and the fourth derivative is equal to 0. Then according to our definition, we're looking for the mth derivative such that the derivative is not equal to 0, but all the lower orders are equal to 0. So looking at z naught equals 2, so f of 2 is equal to 0, and f prime of 2 is equal to 12. So this is the first derivative now where we do not equal to 0, which means the order of our pole, of our 0 then, is equal to 1. So z naught equals 2 is a 0 of order 1. And just in case you're wondering about this last condition, why can't we just stop here? Fm of z naught is not equal to 0, but we need to say each derivative of lower order vanishes at z naught. That's because you can see at f triple prime of z, well, that's not equal to 0. However, f2 is also not equal to 0, so it is not a pole of order 3. It would be, you'd have to go down actually all the way to f of 1, such that f prime of 2 is not equal to 0, but all the lower orders, that is the 0th derivative of the function, is equal to 0. Next, we have this theorem that gives us another way of calculating zeros and determining their order. That is, let a function f be analytic at a point z naught. It has a 0 of order m at z naught if and only if there is a function g that is analytic and non-zero at z naught, such that f of z equals z minus z naught to the m times g of z. We are going to use this example again to illustrate this theorem. To use this theorem, I need to rewrite my f of z equals z minus z naught raised to the m times a function g of z, where this function g of z is analytic and non-zero at z naught. So what I need to start with is I want to factor out z minus z naught to the m. So here, since my z naught is 2, that's where we have a 0 of the function, I'm going to factor out the z minus 2, and I'm left with z squared plus 2z plus 4. So the thing is at this moment, I don't know what order I'm at. I don't know what this m is. But one thing I can tell you is I'm not too thrilled about trying to factor out a z minus 2 squared because it doesn't, factor into this very easily. Also, at this point, the g of z that I have, it is analytic. And I can also see that when I plug in a 2, if I define this as my g of z, when I plug in a 2, z naught equals 2, that I get something that's non-zero. So this is already pretty promising. There's no reason for me to start trying to guess that this is a pole of order 2 or 3 or higher. So as I said, just looking at then the conditions that need to be met. So f is analytic at a point z naught. It has a 0 of order m. Let's see. If we have a function g that is analytic and non-zero at z naught. So this function, it's a polynomial, so it's analytic everywhere. It is entire. So it's certainly analytic at z naught equals 2, and also I have found that g of z naught is non-zero, which means that f of z is a pole of order, in this case, 1. So z naught equals 2 is a 0 of order 1. And in this slide, I just put in the two methods we used. First, here I used this definition of a 0 of order m at z naught to determine the order of f of z. And in this part here, I used this theorem to determine the order of f of z. So I put the two methods here just for comparison. Oh, and one more thing I thought was important to do was go ahead and do one of these other roots that aren't quite as convenient. So I did z naught is equal to -1 plus 3i. So I plugged it into f, and of course it's equal to 0. I looked at f prime, I see that it is non-zero, and therefore this root here is a 0 of order 1. Now using the theorem for this example and looking at the root -1 plus square root of 3i, now I have f of z, I have z minus my root, which is -1 plus square root of 3i, or my 0. And then for g of z, I have the z minus 2, z minus -1 minus square root of 3i. This is what's left once you factor out this term here, the z minus my 0. So g of z is equal to z minus 2, z minus -1 minus 3i. This here is a polynomial, so it's analytic, it's entire, and in particular, it's analytic at -1 plus 3i. And also you can plug in -1 plus 3i into g, and you will find that it is non-zero. And that way you have shown then that this -3 plus no, where is my root? -1 plus 3i is a pole of order 1. I'm sorry, a 0 of order 1. I have not done -1 minus 3i because it's so similar to -1 plus 3i, and I think you can do that on your own. I've been using the word entire function. I figured I should go ahead and define it. It is something we had talked about in our video about analytic functions back in chapter 2, I believe. So an entire function is a function that is analytic at each point in the entire finite plane. And our example was, since the derivative of a polynomial exists everywhere, it follows that every polynomial is an entire function. Our next example to talk about zeros of order m is the entire function f of z is equal to z times e to the z minus 1. And again, we'll start by using the definition. So f of z equals z e to the z minus 1. We're looking for the zeros. So we set the function equal to 0, and it's equal to 0 at z naught equals to 0, both because this 0 here will give us the functions equal to 0, and also when we set this equal to 0, that'll give us a 0 as well. So we kind of think maybe it's of order 2. Anyway, but to use this definition, and actually that guess that I gave you, it's a good way of guessing, but it's no proof. It's not a good way of actually doing the problem. So f prime of z is equal to z e to the z plus e to the z minus 1. F double prime of z then will be equal to z e to the z plus 2 e to the z. So when I plug in z equals 0, f prime at 0 is equal to 0, f double prime at 0 is equal to 2. So this is the first derivative where we start getting non-zero values, which means that this 0 equals z naught is a 0 of order 2. And again, this method here, we use the definition to determine that this is a 0 of order 2. Next, I'm going to redo this problem now using this theorem. So let a function be analytic at a point z naught. That's our f of z. That's great. It has 0 of order m at z naught if and only if there's a function g that's analytic and non-zero at z naught such that f of z equals z minus z naught to the m. So let's guess that our z equals 0 is a pole of order 1. We know it's an order 2, so this isn't going to work out, which is why I wrote this in blue. But let's pretend like we didn't do it this way, and we're using this theorem, and we're going to guess that it's equal to 1. So we're going to have f of z equals z minus z naught being 0, raised to the 1 times g of z, whatever is left over in order to get us our f of z. So that's e to the z minus 1. So g of z is equal to e to the z minus 1. However, now this next condition is that g of z needs to be non-zero at z naught, but g of 0 in this case is equal to 0. So that means that this z naught equals 0 is not a 0 of order 1. So what I'm going to do is I'm going to test to see if z naught equals 0 is a pole of order 2. So I'm going to put z minus z naught squared times g of z. So what's left is g of z is now going to be this function 1 over z e to the z minus 1 when z is not equal to 0, and I'm going to set it equal to 1 when z equals 0. And you can see then, by using this definition of g of z, when I multiply by z squared, I'll get f of z, right? When z is not equal to 0 and I multiply by z squared, then I get z e to the z minus 1, which is great. And then what happens when z equals 0? Well, g of z over here is equal to 1, but when z equals 0, then my f of z is still, this z will give me a 0, and f of z is still equal to 0. So this g of z will work for us here. And we can notice that g of z is entire. We defined it so it would be entire. We avoided that division by 0 by setting g of z equal to 1 when z is equal to 0. And also, we know that g of 0, when we plug this in, well, it's equal to 1. It's non-zero. So we have found our function g that is analytic and non-zero at z naught, and that means our 0, that is z naught equals 0, is a 0 of order 2, because we had to raise this to the second power. Now we are ready to talk about creating poles from zeros. And here is our theorem, creation of poles from zeros. Suppose that 1, two functions p and q are analytic at a point z naught. And b, p of z naught does not equal to 0, but q of z naught has a 0, and it's a 0 of order m. Then what we conclude is the quotient p of z over q of z is a pole of order m at z naught. Our first example, if p of z is equal to 1 and q of z is equal to z times e to the z minus 1. And you might recognize this q of z was our previous example. And we had just found from our previous example that this q of z equals z e to the z minus 1 has a 0 of order 2 at z naught equals 0. But just backing up a little bit, first we wanted to confirm that p and q are analytic at the point z naught. So p of z equals 1, certainly that's analytic. This also is analytic everywhere. They are both entire. Our second condition then, p of z naught does not equal to 0. So here, p of z, well, it's never equal to 0. And then we see that q has a 0 of order m at z naught. So from our previous example, q of z has a 0 at z naught equals 0 of order 2. What our theorem then tells us is p of z over q of z, which is equal to 1 over z e to the z minus 1, has a pole of order 2 at z naught. We have another theorem here regarding poles, which I've made more space and I wrote up here. Let two functions p and q be analytic at z naught. If p of z is not equal to 0, so it doesn't have a 0 at z naught, but q of z has a 0 at z naught, and q prime at z naught does not equal to 0, then z naught is a simple pole of the quotient p of z over q of z, and we can find the residue using this formula. So the residue at z naught of p of z over q of z is equal to p of z naught divided by q prime at z naught. Our first example is going to be f of z equals cotangent of z, and since we want this in the form of a fraction, p of z over q of z, we will rewrite cotangent of z equals cosine of z divided by sine of z. We want to find the residue of cotangent of z. We will start off by saying that the numerator, p of z equals cosine of z, is analytic everywhere, and also the denominator, q of z equals sine of z, is also analytic everywhere. So they are both entire, and for that reason, they satisfy this first part of the theorem. Let two functions p and q be analytic. Next, I'm going to come up here. My next condition, I'm going to select this one here. I'm going to find my 0, where q of z naught equals 0. And that's going to be anytime z naught is equal to n pi, right? Sine is equal to 0 when we have integer multiples of pi. So that's this condition here. Then the next thing I need to check is that p of z naught is not equal to 0. So this is my next condition. So looking at p of z naught, that will be cosine z naught of n pi. Well, that's equal to negative 1 to the n, so that's not equal to 0. So this next condition is met. And finally, I need this last condition that q prime of z naught does not equal to 0. So q prime of z naught is equal to, well, if q of z naught is equal to sine, q prime of z naught is cosine, and z naught at n pi. So this is the same. It's equal to negative 1 to the n, which is not equal to 0. So the conditions of my theorem have been met. What I can conclude then from my theorem is z naught is a simple pole. So z naught equals n pi is a simple pole of my quotient, which ends up being cotangent. Furthermore, I can use this formula to calculate the residue. So the residue at z naught equals, actually it's not 0, it's equal to n pi. I'm so used to putting 0, it looks like, of cotangent of z is equal to p of z naught, which is negative 1 to the n, divided by q prime at z naught, which is also negative 1 to the n. So that's equal to 1. So our residue is equal to 1. For our next example, f of z equals z over z to the fourth plus 4. We want to find the residue. And I just want to say, you can always calculate the residue by calculating the Laurent series, especially if you're extremely fond of them. However, when you see these quotients, I feel like it's worth looking and seeing if these conditions are met, because this residue formula here is so fast and easy to use. Here I've written f of z equals z over z to the fourth plus 4. I identified my numerator, p of z is equal to z, and my denominator equals q of z equals z to the fourth plus 4. And I want to set that equal to 0 so that I can find my zeros of my denominator. I'm going to move my 4 to the other side, so I get z squared then is equal to 2i. Now, I need to be careful here. When I take the square root of 2i, well, the square root of 2, that's good, but I need now the square root of I. And to do the square root of I, I'm going to rewrite my I in exponential notation. And for the square root, I'm just going to raise it then to the 1/2. So I, expressed in exponential notation, is e to the pi over 2. Remember, for our unit circle here, right, we have to come over pi over 2 radians. So this here represents I. Now when I take the square root, I raise that to the 1/2. So I get then e to the I pi over 4 for the square root of I, and then I also have my square root of 2 here. And on my graph, my unit circle now, I'm over here at square root of 2, that's my height, e to the pi over 4 is this angle here. So essentially, what this is equal to, it's equal to 1 plus I, because you see 1 plus I gives us the correct radius, and then the 1 plus I also gives us the correct theta. I'm going to move my graph over here to give me a little more room, and the next thing I'm going to do is I'm going to look at p of z naught and q prime of z naught. So writing this down, now p at 1 plus I now is equal to, well, p is just equal to, p of z is equal to z, so that's 1 plus I. So that's not equal to 0. So I've confirmed this portion of my theorem, and now I need to look at q prime of z naught. So q prime of z naught is equal to 4z cubed, and when I plug in 1 plus I, I'm not actually going to calculate it, but I can see that it's not equal to 0. So my conditions of my theorem are met, so I know that now my z equals 1 plus I is a simple pole, and I can use the formula from the residue theorem to get the residue at z naught of 1 plus I of z over z to the fourth plus 4 is equal to p of z over q prime of z naught. So I'm going to simplify this a little just so that I don't have to simplify algebra later. So my p of z naught is simply equal to z naught. My q prime of z naught, I have that written over here somewhere, is equal to 4 of z naught cubed. So what I have is 1 over 4 z naught squared. So if my z naught is equal to 1 plus I have 1 over 4 1 plus I squared, which is equal to 1 over 8I. And that's my answer. To review what we have covered in this video, we talked about zeros and poles. First, we defined zeros, and in particular, we defined zeros of order m. So we said suppose a function f is analytic at a point z naught. Since f is analytic, then all the derivatives fn at z naught all exist. So if f of z naught equals 0, in other words, this z naught is a 0 of f, and if there's a positive integer m such that the mth derivative at z naught does not equal to 0, but each of the derivatives of lower order is equal to 0 at z naught, then f is said to have a 0 of order m at z naught. And we did this example, f of z equals z cubed minus 8. We found the zeros by factoring. We found 3 zeros. And for our overview, we're just going to work at z naught equals 2. In our video, we also did one of these. We did -1 plus square root of 3i. But at z naught equals 2, so that's one of our zeros. To show that it's a 0 of order 1, we look at the derivatives. So f prime of z is equal to 3z squared, f double prime is equal to 6z, f triple prime is equal to 6, and finally f4 and up, those derivatives are all equal to 0. Well, we're going to evaluate these derivatives at z naught equals 2. So f2 is equal to 0. As we said, that's a 0 of the function. F prime of 2 is not equal to 2. So that implies that this first derivative tells us that the z naught equals 2 is a 0 of order 1. We also have this theorem, a second way of classifying our zeros, of determining what order our zeros is. Let f be an analytic function at a point z naught. It has a 0 of order m at z naught if and only if there is a function g that is analytic and non-zero at z naught, such that f of z equals z minus z naught raised to the m g of z. So for this example here, we also we redid this example using this theorem, using z naught equals to 2. So f of z, so we wrote it in this form, z minus 2 raised to the 1, and then the rest of f was g of z. And we did an example where we had m is equal to 2, so you can see what happens. But in this example, m is equal to 1. We can see g of z is analytic. That's the first condition for g. But it also needs to be non-zero at z naught. So if we plug in 2 into g, we can see that it is non-zero. Therefore, z naught is a 0 of order 1, and it's order 1 because this exponent here was 1. Next, we have these two theorems, which I just couldn't help but put them on my overview slide because yours, being a math major, says you don't ignore theorems. But of course, I did exactly that. I didn't go over these theorems. I ignored them because they we don't use them in problems. They are used to prove other theorems that are useful. So they're useful in their own right, but I did not cover them. But I put them on here because I just felt guilt. Also in this theorem, this e here, it should be an epsilon. Okay, then our last topic was creation of poles from zeros. In particular, we're talking about functions that we can write as a quotient. And in this case, if the denominator of the quotient has a 0, then it's going to be a pole of this function. And we have this theorem here. Suppose that 1, we have two functions, p and q, that are analytic at a point z naught, and b, p of z naught does not equal to 0, but q of z naught equals 0. In other words, it has a 0 of order m at z naught. Then the quotient, p of z, q of z, is a pole of order m at z naught. And then we have the second theorem specifically for simple poles that gives us a quick formula for calculating the residue of a simple pole when we have a quotient. So let two functions p and q be analytic at a point z naught. If p of z naught is not equal to 0, but q of z naught equals 0, and q prime of z naught does not equal to 0, then z naught is a simple pole of the quotient, and the residue z equals z naught of p of z over qz is equal to p of z naught divided by q of z naught. And our quick example was f of z is equal to cotangent of z, which can be written as a quotient cosine of z, sine of z, where now p of z, that's our numerator, is equal to cosine of z, and our denominator, q of z, is equal to sine of z. These are both entire. They're both analytic, so they satisfy this first part of our theorem. Second, we can find where our zeros are, where q of z naught equals 0. That is, q of z has zeros at z naught equals n pi, but we can see p of z naught is not equal to 0 because cosine of n pi is equal to negative 1 to the n, and then also q prime of z naught does not equal to 0. In particular, q prime of z naught is equal to cosine of n pi, which is the exact same thing as p of z naught, which is equal to negative 1 over n. So the residue then of this simple pole of the quotient is equal to p of z naught, which is equal to negative 1 to the n, divided by q prime at z naught, which is negative 1 to the n, which is equal to 1. So that's it for this video. Thank you for watching.